Alrighty, so let's look at IB Chem SL level topic 4.3, covalent structures. This is where we will go beyond formulas and start looking at actual structures, the way atoms are connected and put together in molecules, in covalent structures specifically, okay? So we're going to start with Lewis dot structures, and Lewis dot structures are essentially, it is the tool that we use to figure out how these small molecules are put together. We'll see later on when we get to organic, we kind of take what we already kind of know from what we do with Lewis dot structures and have a much easier way of dealing with organic, well, sort of easier with organic molecules, the larger ones. But for any small molecule, we can use Lewis dot structure to help us determine the most likely arrangement of electrons within the molecule. That's really what we're looking at, right? Because the electrons, the valence ones at least, are the ones that are holding the molecule together, right? Valence electrons are the only electrons that are involved in bonding. So the Lewis dot structure takes the valence electrons, however many you have, takes the atoms, however many you have for this specific molecule we're going to talk about, any one you want to talk about, and gives you a tool to determining how it is probably put together, okay? Alrighty, so example, CO2, formula right there. Well, the structure for CO2 is actually what you see here. It has two double bonds, two from carbon going one to each of the oxygens, right? And if we want to understand the way CO2 is going to behave, we have to know how it is bonded. We have to know its structure. That's the only way we can understand the behavior of that molecule, because the bonding in a covalent molecule is just the base. It is the foundation of everything that molecule is then able to do, and every way that molecule will behave, the properties it will have, and so forth. All right, so let's dig in. So we're really starting with just looking at Lewis dot structures. What are they? How do they do what they do? And how do we determine what they are? Okay, so these are the steps. I wanted to get it all on one screen to start. So if you want to pause and just, copy down notes, go for it. But I'm going to go ahead and walk us through it kind of step by step. And then that should fill in the blanks left from the book or whatnot. Okay. So if we zoom in here and peek, we see that we can start with step one. And just start with step one. Just go step by step. You'll get the hang of it. You won't need to even think about the steps anymore, okay? So step one for Lewis dot structures is determine the total number of valence electrons that are in the molecule. So all you do is you look at your formula, right? And you add it all up. So I know that hydrogen has 1 electron, carbon has 4, and nitrogen has 5, giving me that total, right here, of 10 valence electrons. Note, if you don't get an even number when you are adding up that total, you have done something wrong. At this point, no, period. If you get an odd number when you are totaling valence electrons in a covalent molecule or in a covalent structure, it can't be that way. It can't be odd. It has to be an even number. You will only have pairs of electrons that you're dealing with at this point with covalent molecules. So that's step one, done. Just add them up. And again, only the valence electrons, okay? All right, step two, create the skeleton structure. So the skeleton structure, you can see it there right here, right? It is your basic connectivity, right? What is connected to what? That's it. It's not done yet, right? And everything isn't there, but all of the atoms are there and they are all connected. Okay, that's your starting place. So the trick to doing this is you have to start here with A, right? Determine the central atom. You need to know what atom everything else is connected to. Most of what we start playing with here will just have a central atom with some stuff around it. Even if you have a bigger molecule, you can still think in this central atom way. You'll just maybe have a couple central atoms that are then, connected to each other. And we'll see some examples of that later. All righty, so to determine that central atom, you want to figure out which one it is. So trick is the one that's written first often is the central atom. Not always, but often. The atom that can make the most bonds is almost always the central atom. I want to say always. And if you have carbon in your molecule, it is the central bond, period, end of story, no questions about it. Carbon will always be the central atom if it is there, okay? So for our HCN here, we see that hydrogen is written first, right? Well, that doesn't work, right? Hydrogen is only going to make one bond ever. And well, as far as we're concerned here, so it's never going to be our central atom, ever. Carbon, however, is in this molecule, and we know that carbon will always be the central atom. And if you were to make some Lewis dot symbols, right, just looking at each element and their valence electrons, and then to determine, you know, number of bonds they want to make and so forth, you would see that carbon wants to make 4 bonds, whereas nitrogen only wants to make 3. Therefore, let's make carbon our central atom, okay? All right, so that gives us that skeleton structure. Well, not yet, sorry. Once we get our central atom, then we do step B, which is attach the rest of the atoms to the central atom with single bonds, as you see in the picture there, okay? All right, step 3 is we need to add any remaining electron pairs to those outer atoms to fill all octets or duets, right? Remember, hydrogen is only ever going to have a duet. It won't have more than 2 electrons. So in order to do this, you really want to start with a little checklist in your head, because this is where we're kind of finishing our molecule. And so we want to start double checking as we go, right? So we don't get too far off track, I guess. So we need to always be thinking about the total number of valence electrons, right? We can only use so many, but we have to use them all. And also, are we hitting those octets? Because that's critical. We have to have the octet or duet, and for all atoms, and we have to be using all of the electrons. So let's check it out. So I followed what step 3 said. I added right here, right? I added my electron pairs around the atoms to give me my full octets. So it worked for nitrogen, right? Nitrogen has 8 electrons around it, right? So we have our 1, 2, 3, 4 pairs of electrons, which means a total of 8, right? Get rid of that, so that's not confusing. So we did that part. However, carbon's not very happy, right? Carbon only has 2 pairs of electrons, right? 2 bonds, meaning only 4 electrons. Not going to work. It needs more. So that didn't work. Let's double check the octet. Oh, and that was the octet thing. Oh, and then the number of electrons will have our, right, 2, 4, 6, 8, 10. That gave us our total of 10. So we were right there. Sorry about it, skipping that step. So we have a problem. We don't have an octet on our carbon, okay? So that's where you can come down to the little green notes here, right? This is how we deal with things not checking those boxes on our checklist, okay? If we do not have enough electrons to complete all octets, then make double or triple bonds as needed with the electrons that you have in order to get there, okay? So this is what that looks like. Start with the structure on the left, the one I have underlined in yellow, right? Notice that has those 10 electrons. Look at the structure on the right, the one in the purple circle. That has 10 electrons. So both of those are satisfying the number of electrons, check. However, the one on the left does not have enough electrons around carbon. The one on the right does, okay? So let's look at how we got there. So if I want to drop electrons back in towards that central atom to finish its octet, I can just think of it like, okay, well, nitrogen needs all of those electrons, but carbon needs more too. So what do we do when one thing has everything it needs and another person just needs a little bit of that? Well, if we are nice, we share. So that's what we're doing. We're just doing more covalent bonding. So we are going to take and look and say these electrons are actually going to drop in and form a double bond to keep sharing with carbon. That gets us closer, right? Then carbon would have had, what, 2, 4, 6 electrons, and nitrogen would still have its 8. Not enough, though. So let's take another pair and drop them in. I hope you've noticed at this point that I am always talking in pairs of electrons, either as a bond or as a lone pair, a pair of electrons. They will always be paired at this point. Okay, so if we do those fold-ins, I just like to think of dropping them back in towards the central atom or towards whichever atom you're trying to fix, we then see that we can get this structure, forming those triple bonds. So if we think that every dash, right, every bond is 2 electrons, nitrogen now has 2, 4, 6, 8 electrons, right? And carbon, I'll do a different color for carbon. Oh, I don't like that color though. Yeah, sure, why not? Carbon is going to have 2, 4, 6, 8 electrons, right? 4 bonds equals 8 electrons. And then, hydrogen has the 2. So notice when I'm checking my numbers of electrons, let's just really highlight this point. When electrons are shared in a covalent bond, they count for both atoms in the bond. In case that wasn't clear before, please note that, right? So nitrogen gets all of those electrons. Those are all nitrogen's electrons. It's 8 electrons, valence, right, around nitrogen, it's happy. Carbon gets all of those electrons, right? 8 electrons around carbon, 4 bonds, everybody's happy there. Hydrogen, we'll give hydrogen a different color, why not? Gets those ones, right? 2 for hydrogen, it's happy. Right, so that's the deal with covalent bonds, is that you are sharing those electrons, just in case we kind of missed that piece. All right, now another example of how we could be trying for part 3 here, trying to finish off this molecule and have it kind of not work out right, is what if there are extra electrons left over? So I gave us another example here. I'll just scoot up a little bit again. So on this one, I'm looking at ammonia, NH3. I added up all of my electrons and I get a total of 8, right? 5 from nitrogen and 3 from the 3 hydrogens. I made my skeleton structure. I put nitrogen in the middle because it was both written first and it makes the most bonds. So that makes sense. And so then I just started my checklist, right? As soon as I get my skeleton structure, that's when I'm going to start thinking about my checklist. In the beginning, I recommend writing it down, but that'll fade. You won't have to. So when I look at this, I'm going to see, okay, how many electrons did I use? I used, let's see here, 2, 4, 6 electrons. I have 8. I have extra electrons, okay? So what I would try to do normally is put those on those outer atoms, right? Finish filling in for my octets. That would have been like what I would have been working on, but they're all hydrogens. I can't put any more electrons there, right? So that's where you have to do this second little green note here. If there are extra electrons left over, the outer atoms are all happy, then dump any extra electrons onto that central atom. Okay, and so that is what we did here. So you can see I dumped 2 more electrons right on top of that nitrogen. And by doing that, right, now nitrogen has 2, 4, 6, 8 electrons. It has its octet. Every hydrogen has 2, 2, 2, right? They're all happy with their full octet or duet. Right, so on my checklist, notice I didn't even get all the way down to the octets, and you can look at either one first, it doesn't matter, but I wouldn't have had my octets satisfied either. So yeah, so there you go. You're never gonna check those boxes unless it is correct. That's just the deal. These structures can get more complicated. They can get, you can get kind of trickier ones, and there is a little more nuance to some of these rules that we could dig into. We don't have to, and I am not going to make us because we're tight on time this year. However, just know that as you go further on and look at more complex structures, there is more nuance to these guidelines that can help you determine what is that best structure.